Let's work some problems about basic bipolar junction transistors. First of all, we want to describe the difference in the structures of the NPN and the PNP transistor. So remember that the bipolar junction transistor has 3 layers, and for the NPN, the base layer is the P-type material, where the collector and the emitter are the N-type material. The emitter is heavily doped, whereas the collector is more moderately doped. And the P-type material is very lightly doped. Okay, so for the PNP, it's exactly the opposite. We have the emitter and collector are the P-type material, and the base is the N-type material. And those are the differences in the structure of each. All right, so the next question we're asked for a BJT transistor, if the emitter current is 5.34 milliamps and the base current is 475 microamps, what would the collector current be? And remember, IE is the sum of IC plus IB, because for our NPN transistor, if it was biased to work in the active region, actually let me draw that a little differently. If it was biased to work in the active region, we would have a positive voltage source over at the collector side, and that is RC, which would be driving current into the collector, conventional current. And then we would forward bias the base to emitter junction, which would create a current into the base, and those currents would then combine to be your emitter current. So if IE is 5.34 milliamps, we don't know IC, and IB is 475 microamps, then IC would be 5.34 milliamps minus 475 microamps. So again, just your Kirchhoff's current law equation. Which should be about 4.87 milliamps for your collector current. Okay, next problem, we have a transistor with a collector current of 25 milliamps, and it has a base current of 200 microamps. Determine the beta. So the DC beta is defined as the ratio of the collector current to the base current. So if we have 25 milliamps of collector current for 200 microamps of base current, we're just going to divide that. And that gives us a beta of 125. It's just a ratio, so there's no there are no units there. Another problem where we're asked to find the beta of a transistor, but this time we're given the emitter current and the collector current. But remember, IE is equal to IC plus IB. So if we're looking for IB, we would subtract IC from IE. So we've got 20.5 milliamps minus 20.3 milliamps. Minus 20.3 milliamps. Is this about 200 microamps? Okay, but we were asked to find the beta. So the beta, remember, is the ratio of IC to IB. Now that we have our IB, which is 200 microamps, and we have IC, which is 20.3 milliamps, now we can find our beta, which is 101.5. Again, it's a ratio, so no units for that. Okay, let's move on to a different type of problem. Actually, this is asking for the beta as well. So we know we're going to need the base current, and we know we're going to need the collector current as well. So let's determine how we're going to find that. So we have a voltage of 5 that's dropped across RC. So what they're telling us is we have 5 volts that drops across our 1K ohm resistor. So that's essentially giving us our collector current, IC. So IC is going to be the voltage drop across RC divided by RC. So that would be 5 milliamps there. And then we need IB. So what do we know about IB? Looks like we know that a base current, I forgot to write this in, a base current of 50 microamps. So 50 microamps is applied at the base. I knew I was missing something there. So the beta would be IC over IB, or the 5 milliamps divided by the 50 microamps. Or that beta would be about 100. Okay. Again, so just to review, just to remind you, our emitter current is going to be equal to the base plus the collector currents. Our beta, the DC beta, is the ratio of IC to IB. Okay, so far these are really the relationships we're using in our work. Okay, so for 16, we want to find pretty much all of our currents along with the voltage drop from the collector to the emitter. So just to remind you, the base of our transistor is here, the collector is here, and the emitter is down here. Remember, the emitter is always the side with the arrow, and the base is always the middle that's going into what looks like a gate on the left-hand side. And so let's work through this and see if we can figure this out. Something else that you need to remember is that the voltage drop from the base to the emitter for an NPN transistor should be about 0.7 volts. So keep that in mind. At ground means we're at a zero potential, or that's our reference voltage. So whatever it is, at point B we would be at a 0.7 volt greater potential than whatever we have at E. So if we're assuming that's a zero, that's that would be 0.7. Okay, so let's find our currents here. So IB would be whatever the voltage drop is across RB. So from here to here, divided by RB. So on one side of that resistor, we have 3 volts. On the other side, we have 0.7. So that's the voltage drop across the resistor, which is a 100 kilo ohm resistor. So we've got 2.3 volts divided by 100,000. So that's going to be a pretty small current. And it is. It's about 23 microamps. All right. So now we need to find IC. And in order to find IC, we would need to know the voltage drop across RC, which we don't really know. We know that on one side we've got 10 volts up here. And we know that at the emitter we have 0 volts. But we don't know this VCE, okay? And there's no real way to know that until we find the current through the collector and multiply that by RC. So IC, remember, is also the DC beta times IB. And we are given that the beta is 200. So 200 times 23 microamps tells us that we should have a collector current of 4.6 milliamps. Okay, so we should have 4.6 milliamps here. And that means that the voltage drop across RC would be IC times RC, which is 4.6 milliamps times 1,000 ohms, or 4.6 volts. Okay, so let me make that a different color so we can see it. The 4.6 volts here. So if we have 10 volts here, we drop 4.6, that's actually going to give us our VCE. So let's figure out what that is. VCE would be the 10 volts minus the 4.6, which would be 5.4 volts. Now, we also want to find our IE, but remember, IE is just the collector current plus the base current. So I'm just going to add those two together. So I've got 4.6 milliamps plus 23 microamps. And that's 4.623 milliamps. So just slightly larger than IC. And those are the answers for that one. So for number 17, we're still looking at this same circuit. And we're asked if we increase the VCC, again, which is right here. If we increase VCC to 15 volts, how much do the currents change and how much does VCE change? So first of all, remember how we found our IC. So first of all, with IB, we found IB by taking our 3 volts and subtracting the 0.7 drop here. That's not going to change because VCC changes. That's not different. So IB is not going to change. Also, we used our beta and our IB to find IC. Again, that's not going to change. So we're still going to have our 4.6 milliamps there. And again, that's not going to change the voltage drop across the resistor because the current would have to change for that to change. So what is going to change is VCE is going to change. So VCE now would be, instead of 10 minus 4.6, it would be 15 minus 4.6 because we've increased that voltage. So VCE now would be 11.4 volts. So it actually would be, let's see, 4.6. So it would actually increase by 5 volts. So VCE increases by 5 volts. Okay, so that's all that really changed if we increase the VCC in that question. Okay, for 18, we want to find our currents here, IB, IC, and IE, and beta. So we're not given beta this time. What we are given is the voltage drop across the collector to the emitter. So that's going to help us figure that out. So first of all, let's look for IB. Now remember, IB is going to be the voltage drop across RB. We've got this drop over here of 0.7 volts. So the voltage drop across RB would be the 4 that we have on the left-hand side minus the 0.7 drop we have on the right-hand side over 4.7 kiloohms. Let's calculate what that is. Um, 702 microamps. Now we don't know beta. We're going to have to find IC another way. But we do know that IC would be the voltage drop across RC divided by RC. And of course we know RC is 470 ohms. Now what's the voltage drop across there? We have 24 volts on the right hand side minus, remember at the emitter we've got 0 volts, and then we see a plus 8 going in this direction. So at this point we'd have 8 volts. So on one side of the resistor we have 24 volts, on the other side we have 8. So 24 minus 8 over the 470 would give us that. And that gives us about 34 milliamps. IE would just be the sum of IC plus IB. So 702 microamps plus 34 milliamps. And that's about 34.7 milliamps there. Now we do want the beta. So remember, the beta is defined as the ratio of the collector current to the base current. So we've got 34 milliamps divided by 702 microamps. Which gives us about 48.43, and that would be the beta. All right, for 19A, we're looking now for VCE, VBE, and VCB. So we're going to need to find our voltages at C, at B, and at E, because remember, VCE is defined as the voltage at the collector minus the voltage at the emitter. Or you could also think about it as if I put a voltmeter here and I put the red lead at the collector and the black lead at the emitter, that's what we would measure there as well. Okay, so I'm going to get rid of that. All right, so we need to find our voltages at each of those points. At the emitter, we have 0 volts because the emitter is tied straight to ground. So I'm just going to make a list over here. We know that VE is 0 volts. The voltage at B, remember for this NPN, we have a drop of 0.7 volts from the base right here to the emitter. I'll identify the collector as well. So when we go from the emitter to the base, we're seeing a voltage rise of 0.7. So we should have 0.7 volts there. And now we need to figure out what we've got for the collector voltage. Now, this is going to be a little more difficult because we need that collector current to find this out. So let's look at what our base current is, because we know that we have a beta of 50. So let's go back and find our base current. So IB is going to be the 5 volts on one side of RB minus the 0.7 volts on the other side, divided by 3.9 kilo ohms. And that gives us about 1.1 milliamps. Okay, just checking behind myself here. And we know that the beta is 50, so that means that our IC would be beta times IB. So 50 times 1.1 milliamps means that we would have 55.13 milliamps of current for IC. Now, the voltage at the collector is going to be our VCC minus whatever the voltage drop is across RC. So that's going to be IC times RC. So 15 minus the 55.13 milliamps times the 180 ohms of resistance will give us our IC. And that gives us right about 5.08 volts there. Okay, now we're ready to find our VCE, VBE, and VCB. So again, we're just going to utilize our definitions here. VCE is VC minus VE, where VC is 5.08 and VE is 0. So 5.08 volts. VBE is the voltage at B minus the voltage at E. And remember, we have that 0.7 volts minus 0 volts at E. So 0.7. And then VCB, VC was 5.08. And VB is 0.7. Which is about 4.38 volts. Okay, so those are your answers for that one. All right, so for part B, now this time we see that our voltage sources are turned around. They're both swapped into the opposite direction. But we also note that the arrow here at the emitter is pointing in, which makes this a PNP a PNP transistor. So remember, that means that we've got P-type material here at the collector and at the emitter, and we've got N-type material here at the base. So in order for this to be operating in the active region, we need the base to be positive or forward biased. So we would have to have the negative terminal of our source connected at this point, which we do. And also, in order to be working in that active region, our P-type material at the collector, our P-type material here at the collector needs to be reverse biased. And as we can see, it is because it's connected to the negative terminal into the P-type material. So that's actually working in the, that actually should be working in the active region. So just might want to think about that when you start to work through these problems. But we're looking for the same thing here. we're trying to find VCE, VBE, and VCB. So again, we need to find all of those voltages individually. Okay, so VE, we already know that that's connected straight to ground, so that's going to be 0 volts. VB is going to be, so remember, for the emitter, the NPN base to emitter junction, that's going to be a drop of 0.7. For the PNP, it's actually a reverse polarity. So the drop occurs from the emitter to the base in the PNP. So it's just flipped. So from 0 to negative 0.7 means that we would have a negative 0.7 volts at point B. So we still want to find our current. Let's see, for 19, are we given a beta? Yes, we are. We're given a beta of 125. Let me write that on the drawing here. Okay, because we're going to need to know that, either that or we would need to know the VCE, but one of those two we would need to know. Okay, so to find IB, remember on on this side we have a -3, so -3, and then on the other side we have a -0.7 of RB, and then we're going to divide by 27 kiloohms. So -3 minus a -7 is the same thing as -3 plus 0.7. Or -2.3. Okay, let's calculate what this would be. That's about 85.1 microamps. And since we know the beta, we can multiply IB times the beta. So that 85.1 microamps times the 125 will give us that. So that means we have about 10.65 milliamps for the collector current, and that's going to be going through this direction up here. That will give us the voltage drop across RC. IC times RC using Ohm's law, so 10.65 milliamps times 390 ohms is about 4.15 volts. Now that voltage drop is in this direction, 4.15 volts. So again, we've got 0 volts here, 0 volts here. When we go back up this way, we are dropping 8 volts. So at this point, we would have a -8 volts. And then this drop of the 4.15 in that upward direction means we're actually adding it as it goes back down. So what that would leave for VCE is the -8 plus the 4.15 volts. So 3.85. All right. So let's move on to number 22. Just have a few more. First of all, I want to check that answer real quick. So just pause if you need to, or rather fast forward a minute. Let's see. 3.13. Oh, I didn't find everything, did I? So VE, VB, VCE I found was negative 3.85. VBE was 0.7. And then VCB, at VC, we have negative 3.85. And at VB, we have minus 0.7. So VCB would be about 3.15. Okay, so a couple more problems here. Here we're looking for all of our voltages, and it looks like we only have RE in this circuit, so we only have a resistor at the emitter, which is different from what you might be used to. But think about our voltages here. So at B, we don't see a voltage drop from that VBB source. So we would have a plus 10 volts here. So VB would be plus 10. At the collector, same thing. We don't have a resistor to take any voltage drop. So right at C, we would also have 20 volts drop there, which is our VCC. Now at VE, VE is going to be VB minus 0.7, because we're going to see that drop from here to here of 0.7. So 10 minus 0.7 would be 9.3 volts. Now VCE, again, is just VC minus VE, where we have 20 volts minus 9.3, or 10.7 volts. VBE, again, that's just a drop of 0.7. VCB is VC minus VB, where we've got 20 volts minus the 10 volts that we have at B. So that difference would just be 10 there. Similar for 22B, we have a negative 4 at B. We have a negative 12 at C. And remember, this is a PNP, so we would see the drop in the opposite direction of that 0.7 volts. So V at E would be the minus 4 plus 0.7, or minus 3.3 volts. So again, if we're looking for VCE, that's the definition is VC minus VE. So don't worry about the signs so much. Just if VC is minus 12, write down minus 12. Minus whatever VE is, which is a negative 3.3. So that would be negative 12 plus 3.3, which would be about negative 8.7 volts. And then VBE, of course, would be a negative 0.7, and VCB would be minus 12 minus the minus 4, or about 8 volts. All right, so for 31, we're talking about finding the saturation current. Now, the saturation current is basically the maximum current we're going to see, and because once we get to that current, we're at saturation. So what is that? Saturation occurs when the current through the collector just dumps straight into the emitter. If we're talking about electron current, it would be the other direction. But for conventional current, we're talking about that current going straight down. And what that means is that our VCE would be about 0. As a matter of fact, they even tell us, assume that it's 0. Some in saturation, they would say you could assume a small voltage there, but technically we look at it as if it's a short circuit, which would make that voltage be 0. So if that's the case, then what we would be measuring at this point would be 0 volts. And so the current IC would be 5 volts minus 0 divided by the 10K. Okay, so that would be about 500 microamps. So IB would be IC divided by beta. So the 500 microamps divided by 150. Or about 3.33 microamps of current there. Okay, so that this is the current that we would need to apply at the base in order to get to be at that saturation point. Now, if we had 3.33 microamps of current coming in at the base, that's going to tell us what this voltage drop needs to be. So to find that, the voltage drop across RB, I'm going to take IB and multiply by RB. So that 3.33 microamps, we would multiply that by 1 mega ohm. And that's going to give us about 3.33 volts right here. Now, that's not exactly what we need at VN, okay, because remember, we also need this junction to be forward biased by about 0.7 volts. So what we would need VN to be would be VRB plus that VBE, which is 0.7. So 3.33 plus 0.7, or about 4.03 volts there. Could be the input voltage for that one.